All right. So one thing that we know from earlier chemistry is that acids and bases can be used to neutralize each other. All right. We're going to talk a little bit more about that specifically here. So in a neutralization reaction, you're always going to get the same thing. You're always, when the acid is reacted with the base, it's generally going to give the same two products. It's going to give what's considered a salt and water. All right. And when I say salt right here, I don't literally mean sodium chloride. A salt is, in chemical terms, is an ionic compound formed from the anion of an acid and the cation, which is generally a metal, of the base. All right, so classic, just generically, you could show it like, all right, pretend this is just a generic acid. This is a base, that's a metal hydroxide, and the H plus from the acid is going to react with the hydroxide here to make water. And then the salt is just what's left over. All right. The most classic example would be if you reacted sodium chloride, hydrochloric acid with sodium hydroxide. And again, your water comes from the hydroxide and the H plus. And then the salt is just the anions that are left over. It is the cation from the base with the anion from the acid. All right. So most of the neutralization reactions that we're going to be concerned with are going to be a 1-to-1 ratio, but there are cases where it would not necessarily be 1-to-1. All right. So we're going to go through the different scenarios that you're going to be responsible for. All right. So the first, the most famous examples generally involve a strong acid with a strong base. And so some examples, when we talk about strong bases, generally what this means are hydroxides. All right, sodium hydroxide, potassium hydroxide, lithium hydroxide. These would be examples of strong bases. All right, there's a couple of hydroxides that aren't generally considered strong bases, things like magnesium hydroxide, beryllium hydroxide. And the reason that they're not considered strong bases is that they're just not that soluble in water. All right, and in order to be a strong base, it has to be something where if you added it to water, it would generate hydroxide ions. All right, and if they're not that soluble, they're not generating a whole lot of hydroxide ions. All right, calcium hydroxide is a little bit of a borderline base. All right, it's definitely basic, but as to whether it's considered a strong base or not, there's some argument there because its solubility is somewhat intermediate. All right, so let's look at that first case of an acid plus a metal hydroxide. All right, so an example of another example of a strong acid would be something like nitric acid. Here's its formula, and strontium hydroxide. All right, where that's an example of a strong base. All right, and one way to get the neutralization ratios correct is just to remember that you're always going to be making water. All right, so let's pretend that this 2 right here wasn't there. All right, let's try to figure this out. We know that when water gets made, it's going to link the hydroxides with the H pluses. All right, so notice that from this formula there's 2 hydroxides. So what that means is that we need 2 H pluses over here to pair up with these hydroxides. That's why we need this 2 here. All right, and when 2 of these H pluses pair up with the 2 OHs that exist here, that's going to make 2 water molecules. All right, and then your salt is just going to be everything that's left over. All right, it's going to be your strontium ion from here and your nitrate ions from here. Notice you have 2 nitrate ions, and that's why when you do the formula, it's going to be like this. All right. So another example, common example, is when an acid reacts with either a carbonate or a bicarbonate. And a bicarbonate is sometimes called a hydrogen carbonate, but most of the times I would argue that chemists call it bicarbonate. For example, NaHCO3 is just common baking soda, and most people call that sodium bicarbonate. All right. So when this happens, it's going to yield a salt plus water and carbon dioxide. All right. One thing I want to point out is that the reaction actually happens through a temporary production of H3 or H2CO3. This is carbonic acid, And this is very unstable because it immediately wants to decompose to make water and carbon dioxide. So if you just want to think about this reaction, if you reacted HCl with sodium bicarbonate, and notice it's got it's got the part right there. When you hear that bicarbonate, you should think, okay, it's going to be one of these types of reactions. All right. So what's going to happen is that the H plus here is going to link up with the bicarbonate ion to make H2CO3. All right. But remember, when H2CO3 gets formed, it immediately wants to break apart to make H2O and CO2. So you're going to see a vigorous bubbling whenever this reaction happens. All right. This is the classic. This reaction right here is the classic baking soda and vinegar reaction. Actually, it doesn't use acetic acid, but it looks exactly the same. You're going to see that vigorous bubbling. All right. So one thing that's going to left over, notice you still have a sodium ion and a chloride ion. So sodium chloride is going to be one of your byproducts here. Okay. So another reaction. What if we were to react nitric acid with this compound right here? This would be potassium carbonate. All right. So notice it contains carbonate right here. All right. So either carbonate or bicarbonate, you're going to get the same thing. All right. So the thing is, whenever you hear those, remember you're always going to end up initially making H2CO3. So if you take a look at this CO3, well, how many of these guys right here would we need to make this? All right. Well, each of these only has one H plus. All right. So in order to make H2CO3, we're going to need two of those. All right. So that when those react, it makes one of these right here, and again, that immediately breaks apart to make water. And carbon dioxide. All right. And then your salt's just going to be whatever's left over. All right. Well, let's see what we have. All right. Notice we've got 2 potassium ions from this, and we would have 2 nitrate ions. All right. So that's going to end up making 2 potassium nitrates. All right. And this is just going to be, the potassium nitrate is just going to be dissolved in the liquid. All right. So you wouldn't actually see the solid. It would just be a solution. If you were to completely evaporate that solution after you neutralized it, you could isolate this as a solid. All right. Next reaction is the reaction of an acid plus a metal oxide to yield a salt plus water. All right. So one way to think about this reaction, which I think helps it to make sense, is just to think about oxide as oxide is obviously the anion of oxygen, but think of it as water just without 2 of the H pluses. All right, this is the Lewis structure of water. And if we took away an H plus here and an H plus over here, this is what you would have. All right, you would have oxide. All right, so when you see some sort of oxide, just realize for every unit of the oxide, you're going to need to add 2 H pluses to it to get the water, which is what you need for the neutralization. All right, so if we've got potassium oxide, notice that there is just 1 oxygen. That means we're going to need 2 units, or somewhere we're going to need 2 H pluses to neutralize it. All right, so we can do that this way. That ends up the H pluses combined with the oxide to make water, and then your salt is just going to be whatever is left over, which is going to be potassium chloride. All right, notice I should have put aqueous in parentheses here. Same thing here, same thing here, just so that you're doing your reactions correct. All right, and the last example of a neutralization reaction, which you're responsible for, is the reaction between an acid plus ammonia, and that's going to give what's called an ammonium salt. All right. And so one thing about this is it's a little bit of an exception to that general rule that you end up making water. All right, because this is an acid-base neutralization that can happen without water being formed. All right. So in this particular reaction, all right, if we had ammonia, which is a weak base, all right, and you reacted it with HCl. All right. There's actually two ways that this reaction could occur. It could either happen in its gas form, but it could also happen in solution. All right. So I'll give an example of both of those. All right. So notice, so when this happens, all right, notice that ammonia has got a lone pair right here, and this is an acid right here. And so mechanistically, what could happen is that lone pair is going to essentially act as a Lewis base. Sorry, right, a Lewis base. All right, so it's going to attack that H plus. That makes a chloride ion. That makes these two ions, and they're going to be attracted to each other because of their opposite charges, and that just makes ammonium chloride. All right, that's just a common ionic compound. All right, so actually I made one mistake right here. I said G right here. That should actually be S. Ammonium chloride. If the gases are combining with each other, that would make this as a solid. All right. So one way that you can demonstrate this reaction is if you had a container here that contained ammonia. All right. You can actually buy ammonia dissolved in water in the grocery store. All right. It's a common cleaning chemical. All right. And in a separate container, if you had HCl, just hydrochloric acid. All right. And you connected these two solutions with some sort of tube. All right. Well, if we heat both of these, or even if we don't really heat both of these, so ammonia in its pure form is a gas. So some of that gas can just come out of solution, and it's going to want to travel up this tube here. All right. Some of the HCl, remember HCl in its pure form is a gas. It can travel up this tube, and what you end up having is you're going to see this white powder form right here. All right, and I'm going to include a link to a video which shows how that white powder gets formed just by these two solutions getting close to each other. All right, but alternatively, if you just took these two solutions right here and just mixed them directly with each other, all right, took aqueous ammonia and aqueous hydrochloric acid, and you mix them with each other, you would end up having the same reaction occur. But you would just have these ions right here swimming around in the water. All right, and the way that you could describe that is just say that you have aqueous ammonium chloride. So remember, when you have an ionic compound which is aqueous, what you actually have is just the free ions. All right, if you wanted that solid white powder, which is pure ammonium chloride, all you would have to do is evaporate the water off, and it would leave that powder. All right. So these are the neutralization reactions that you're responsible for. Make sure that you are able to recognize those and to balance those types of equations.